Welcome back. So now we have David's second lecture on monoidal categorification of cluster algebras and quantum affine algebras.
Okay, so let me briefly recall what was discussed yesterday. So we consider two families of algebras associated to G, which is simply laced. Lie algebra and parameter, which is not a root of unity. So we have some algebras. So UQ G, Q deformation of the universal enveloping algebra of G, and then UQ LG associated to the loop algebra, which is now an infinite dimensional Lie algebra. And so in both situations, we looked at the category of finite dimensional representation. So here I denoted it by CF, and here we have category C. So these are tensor categories. Of a finite dimensional module. Okay, and so in this case, I recalled that it's very similar to the representation theory of G. So it is a semi-simple category. Braided. And this one is not. It's not semi-simple, not braided. So I will give an explicit example today where we see this defect of symmetry of the category. And in fact, this is exactly where cluster symmetry comes with this kind of defect of braiding in the category. That's a phenomenon related to this that I will discuss. So we have also discussed the parametrization of simples. So I continue my kind of table here. So here we have some module, highest weight module, as this morning. So parameterized by dominant weight of G, the classical Lie algebra. And here instead, the parameters are Riemann polynomials, so n tuple of polynomial. Okay, and then we have the fundamental modules, so subfamilies, fundamental. The subfamily of simples. So here, let's say Vi, which is attached to omega I, a fundamental weight of G. And what plays a role for us, a fundamentals module here are so VIA defined as the simple representation associated to a family of polynomials, which is almost trivial. That is to say, all of them are one except one, which is of degree 1. So it is attached to family. This is a position I. But now, as it's a polynomial, this degree 1 polynomial has some root. So the A is the inverse of this root. In fact, it's a parameter for this family, continuous family of simple of simple modules. And so both play the role of fundamental modules, also in the sense that they generate freely the Grothendieck ring of the category. So here, so K0 of CF. We will be interested in these lectures a lot on Grothendieck rings, their structures, relating them to cluster algebras. So this one is polynomial ring in these classes. That things I explained yesterday, so which Xi is the class of I. And so this one is larger. And XIA is the class of this fundamental module. So these are not trivial results based on character theory in these cases. But we can notice here that it's commutative. So that's where I stopped yesterday. Also, the category is not ready. So this is parallel here, but it's in some sense it's a bit hidden that the category here has some degree of complexity that we do not have here because of the semi-simplicity. Okay, so are there questions on this? So I would like to first to discuss now some examples of two-dimensional modules to see how what happens here. So, examples. And to see maybe some first hint of the cluster structure in two-dimensional representation. So let me first so for completeness, look at SL2, standard SL2. So we have the representation, natural representation. Let's not by V plus and V minus the highest weight and lowest weight module of this representation. So in this case, so maybe we can put this V. And so V tensor V is, as we discussed yesterday, it's not simple, so this is well known, and we have a decomposition as some. So we have the symmetric and skew-symmetric tensors, which gives the decomposition into simple modules here. In fact, it's true for any Lie algebra. You get a decomposition. The two parts are not necessarily simple, but it gives decomposition. So, so more precisely, so here we have the subspace V plus tensor V plus tensor V minus plus V minus. Okay, so that's a submodule of dimension 3, and then we have V plus tensor V minus. So that's the decomposition into semi-simple. This is just SL2, for example. So equal 1 if you want, yes. Classical. Just to see the difference. And of course, the flip is an automorphism of the representation. That's an automorphism. So again, this is not specific to this representation. It's true for any representation of any algebra. Okay, so now let's look at the quantum group analog of this picture. So let's take UQSL2. So again, we have a two-dimensional representation. So this is the fundamental representation V1 that we discussed here. So V1. So I will keep the same notation for the basis. So we can write the action explicitly, so that if you want to compute something. So UQSL2 has generators E, F. Okay, and so here the action, so I write here so by 0, I mean that E applied to V plus is 0 here. So here we have V plus, here is Q minus 0, and the eigenvalue of Q, of K are Q and Q minus 1. So if we had just classical SL2, I would put a H here and just V plus and minus V minus. It's quantized. The eigenvalues are Q and Q minus 1. You can check easily that it's the defining relation of UQSL2 are satisfied by this. Okay, so now we may want to see the same thing as we had here. I can write it. Well, I continue the example. So we look at V1 tensor with V1. So again, it will decompose as a sum of two representations, but because of the coproduct, which is not symmetric, if you remember the coproduct, when you act on the V plus tensor V plus, you do not get this one, but there is some factor Q which appears for one of the terms. Okay, so you get, you have V plus tensor V plus, and then if you look at the next vector, you get V plus tensor V minus plus Q minus 1. Minus tensor plus. Okay, plus a one-dimensional subspace. And again, it's twisted because of the formula for the coproduct. So here you have minus Q minus 1, V plus tensor V minus, plus minus. So here you have. But still, this is a decomposition into submodules, the direct sum of two submodules that are simple. But so that's the first point. But now, if you look at this decomposition, you see that, for example, this one-dimensional subspace is not stable by the flip. And in fact, the flip is not an automorphism of V1. So that's so there is still a braiding, but it's Q-deform. And in fact, you may write explicitly the matrix. So we have, let's say, 2Q. It's an automorphism of UQSL2 module. And you may write matrix, 4 by 4 matrix, this way. It's a basis on pure tensors. The matrix. In the basis of pure tensors. So it's very close to be the matrix to twist, but it's Q-deform. So here you have Q, 0, and 1 minus Q. So up to a factor, in fact, that's the braiding which comes from the universal R matrix. So at Q equal 1, you get the flip, but it's not the flip for generic. So that's something you can check also by hand, that this is indeed an isomorphism of this. Okay, and so let's continue now with the quantum affine situation. Let's look. Or any question on this? No, it's not a coincidence. It's a general theorem for simple finite dimensional Lie algebra. The dimension of simple modules for the quantum group and the Lie algebra are the same. In fact, the character match, the decomposition of tensor product match for finite dimensional Lie algebra. So it's different for loop algebra, but so it's not a coincidence at all. So in this case, we check by hand that it is semi-simple, we get the decomposition. But it's a general. Sorry? That's maybe Sachin knows about it, but well, if you want to preserve the Hopf algebra, so if you put some constraint, I think there is a uniqueness theorem.
This representation is the two commands. You have two dimensions and you have
for the braiding.
This example.
Yeah, for this example.
So
Yeah.
one like that.
Yes, if you want to deform the category with all its structure, then there is some uniqueness here. So it's not completely artificial deformation in this sense. Right? Okay. Okay. So let's go now to the loop case. So loop L SL2, and we can also do things explicitly here, thanks to what I explained yesterday. We have this evaluation morphism, okay, which I recall. So here you have generators E0, F0, Q1, F1, K0, K1. And the respective images are so Q minus 1 F, which should be Q minus 1 E, E, F. So that defines a surjective morphism. And so I think I explained it yesterday already. So V1 of A is the pullback of this representation by this morphism. So it's pullback. K0 and K1, yes, because we look at the loop algebra. So the central charge classically is sent to 0. Well, we could have a central charge, but then it acts trivially on finite dimensional modules. Okay, so P1. So we can complete the table, which is still here. Maybe I can do it here. Now I look at V1 of A, same basis. So this is the action of A1, F1, K1, but now we have also E0, F0, K0, and here, so we have still 0. Now it's K minus 1, no, sorry. So it's F, so it's K minus 1A minus 0, 0, K minus 1 A plus Q minus 1 V plus Q. So we get all operators in this two-dimensional vector space. And you see that it depends. So it should be consistent with my notation. So it should be Q minus 1 A and Q A minus 1. So in fact, this is also where you can check here directly that these representations are not isomorphic one to each other. So for example, you can compute, you may compute, for example, the action of E1 composed with E0 and see that it is a diagonalizable operator, and the spectrum is given by 0 and K minus 1A. So you see that if two of these representations are isomorphic, then the spectrum of E1 composed with E0 will be the same. The value of the spectral parameter will be the same. Just a side remark. Okay. Okay, good. So now we may. I just wanted to say that just by looking at this explicit action, you can check by hand that V1 A is isomorphic to V1 on B if and only if A is equal to B. So which is a part of the theorem of classification, but in this case, you can check it just by looking at the eigenvalues of E1 composed with E0. And the eigenvalues are 0 and K minus 1. It's not completely unrelated to the general proof. One of the eigenvalue of Greenfeld generator. Anyway, so that's just enough. So we know explicitly this module, and so we may want to investigate tensor product as the structure of V1 and A tensor with V1 B. And in fact, it's quite interesting structure. So what we know already is that if we restrict the action to UQSL2, we have only two proper subspaces which are submodular. So I will denote it by maybe W1. So it contains W1 exactly two proper submodules. As a UQSL2. So now we have an action of a larger algebra, and we may wonder if these submodules are still submodules for the larger algebra. Okay. So now it's a bit. So let's say this part is. Okay, so we may first ask UQSL2. No, UQSL2. So our algebra UQSL2 contains UQSL2 in the same way as the loop algebra contains SL2, and we have already investigated the structure for this algebra. So this is what it's here. Because in fact, this inclusion of UQSL2 into UQLSL2 is an inclusion of algebra, but also of Hopf algebra. It is a sub-Hopf algebra. So when you look at tensor product of representation here, the restriction to UQSL2, the structure of representation will be the structure of the tensor product restricted to this level. Everything is compatible. So we have looked at the structure of the representation for UQSL2. We found a decomposition in two submodules, direct sum of two submodules which are not isomorphic. So these are the two subspaces, only two subspaces which are submodules. Only two proper submodules. So now if we want to know the structure of this module, if there is a submodule for the action of the large algebra, it should be a submodule for the action of the small subalgebra. So we have two candidates to be a submodule, W and 1. Only, so I can write it W and 1. So the only two possible submodules. Okay. In fact, most of the time they will not be submodule, but sometimes yes. So now let's look both of them and start ask the question: is it a submodule? So we check if or not. These are submodule for the action of the whole algebra. And in fact, it's in this case quite easy to do. So let's look for W. So W is generated by the tensor product of the highest weight vector. So what we can do, we take again this tensor product of highest weight vector, but instead of applying F1, we apply E0. And we see what we get. So we apply E0 on V plus tensor V plus. So again, it's easy to do it explicitly thanks to the coproduct formula. So everything is explicit. And well, I did it for you. So you get, so here you have two parameters, A and B. And what you obtain is a Q minus 1, V minus tensor V plus Q minus 2, V plus tensor. So A and B both appears because you look at the action of E0 and the two spectral parameters. So now when you look at this vector, if W is a submodule, then it should be up to a scalar equal to this vector. So now you can see that it gives a condition on A and B, which we can write explicitly. And in fact, so we obtain that W is a submodule. So if and only if, so A divided by B is equal to Q minus 2. So that's the condition so that this vector is in W. So if this condition is satisfied, it's a submodule. Otherwise, it's not. And so we have just one other possible submodule. And so we can do the same for 1. Okay, and so you can do the same. You apply F0 on this vector here. Generate this one. So it's really explicit linear algebra. And which is my minus 1 is minus tensor V plus. So you compute and you obtain that it is 0 if and only if A divided by B is also a power of Q, but not the same. You obtain Q to the 2. I did some switch. Yes, sorry. So it should be the same as. Okay. So now again, so one is a submodule. We obtain this condition. If and only if. And so now we see that we have three different situations. So if three situations, so the first one is when none of these conditions are satisfied. So if so this is called a generic situation. In this case, the two candidates for being a submodule are not submodule, and so the tensor product is irreducible. No. That's first conclusion of this. Not in particular that it includes the case when A is equal to B. So V1 of A tensor square is simple, which is something that we did not have in the previous. So in particular. Now we may look at the case when it's equal to Q minus 2. So then in this case, we obtain a unique proper submodule, dimension 3. As a unique submodule. So it is of dimension 3. And in particular, this representation is not semi-simple because it has a unique proper submodule. And we can look in the reverse order. So then it has also a unique proper submodule, but now not of the same dimension, of dimension 1. And it is not semi-simple. So we get an example of a non-semi-simple modules, dimension 4 in this category. But we get also a counterexample for the braiding, also from this. So we obtain mark that so V1 if I want to keep the notation, Q2. Then it's not isomorphic. For any A, because this one has a unique proper submodule of dimension 1, and this one unique proper submodule of dimension 3. This one unique proper submodule of dimension. So they cannot be isomorphic. However, we may look at Jordan-Holder composition series for these modules. And I will write it more space. So if we look at the first one, so this is V1. Okay. So it has a unique proper submodule of dimension 1, so that's 1. And it has a quotient of dimension 3, which, so I will denote by W of A. So this is a unique quotient of dimension 3. And in fact, this quotient appears to be isomorphic to the submodule of V1 of A tensor V1. And the quotient is subdimensional. You have such exact sequences in the category. So that's something so either you know that the Grothendieck ring is commutative, so they have to be isomorphic. But if you don't know it, you can check also explicitly that this quotient is isomorphic to this submodule. So they are not isomorphic. These are non-splitted exact sequences. Non-split. Exact sequences in this category. And now, of course, in the Grothendieck ring, the images are the same. So V1 in K0 of C. So V1. Okay. So this is 1 plus W. And it is the same as AQ2. And of course, by definition, this is a product. Sorry? That's the product of the two Drinfeld polynomials. So this is 1 minus A. And in fact, it is also an evaluation module, but from a three-dimensional simple module of UQSL. So the highest weight is 2. That's it depends on A. And here you get a relation in the Grothendieck ring, which looks very similar as exchange relation we had this morning in the talk of Clara. A product of two, which is a sum of distinguished elements, which is a sum, again, of two distinguished elements. So that's, in fact, the first instance of exchange relation, I think. We'll see more. And in fact, as I hinted a bit, it's related here to some defect of symmetry of the tensor product, and also the fact that you have non-semi-simple. Okay, because if you take different parameters, the tensor product is just simple, so you have no relation in the bottom. But here, just at this point, you have such a relations. Okay, so maybe it was a bit longer than this example. What's expected? So it's a theorem of Chari and Presley for SL2. For SL2. But for SL3, it's not true. So that's specific. Any simple module of UQL, finite dimensional simple module of UQL SL2 is real. It means its center square is simple. So okay, so now I wanted to state some, still for SL2, some generalization of this. Okay. Okay, so in fact, there is a description of all simple objects for UQL SL2. So simple finite dimensional. So here we had already some examples of this, but it can be generalized. So first thing we will do is we will denote by V and A. So that's the evaluation module. Or maybe this notation is not so good. Okay. Evaluation presentation of UQL SL2, so obtained from simple modules of highest weight n omega 1. So obtained from the UQ SL2 simple and yeah. Okay. So that it generalizes what we did for the fundamental modules. L1 of A in just V1. Okay. Fundamental. Okay. And so there is some first theorem. Chari Presley, which is there is a factorization of any simple modules into such modules. So any simple, let's say V in C can be factorized the following form. So V isomorphic to L and 1 and R. It can be factorized as a tensor product of evaluation modules. Okay. So remark. So when this tensor product is simple, then in fact the factors commute. So it's a unique factorization. Second point is that not all such tensor products are irreducible, as we have seen already. So any simple modules can be factorized in this form, but not all modules of this form are simple. And, not all such products. And so third remark. So this is for SL2. So for SS3, this kind of statement does not hold. So this is really for G. So it's untrue that any simple modules of UQL SS3 is a tensor product of evaluation. So the order does not matter. So that's a way to say it. Yeah. Otherwise, we may say that there are well-defined grading in the category when such tensor products are simple. But yes, the order does not matter. Sorry? I cannot hear you. For higher rank the algebras. No, the whole statement. There are things that work, but we cannot factorize as tensor product of evaluation modules. So all these modules here are evaluation obtained from simple modules of UQSL2 by evaluation. So for SS3, for instance, there are evaluation morphisms, there are evaluation modules, large family of simple modules obtained this way, but it's known that there are some simple modules that cannot be factorized in this way. For SS3. R is a number of factors here. So I will just explain now. So this factorization can be made explicit. So it's related to some combinatorics, which are again related to cluster algebras that we discussed. Also, this is much before cluster algebras, result from the 19th. In fact. Some cluster algebras are hidden in it. So yes, so how to write such a decomposition? So we can, so there is a notion of Q segments. So let's following. So let's define N. Okay. So this is the following set of complex number: A to 1 minus N, A to 3 minus N, to N minus 1. Okay, so these are the roots of the Drinfeld polynomials of this representation, the inverse of the roots of the Drinfeld polynomials. Of the Drinfeld polynomial. Of L and A. And this is called a Q segment. So that's a finite subset of complex numbers with a specific form, just a subset of theta. And so now, if there is a notion of being in a general or generic position for such Q segments. So if we pick up sigma 1, so Q segment. So we will say that there are in so sigma 1 and sigma 2 are in general position. So by definition, that's the definition. So if and only if the union of these two is not a Q segment, it's not. So it's not of this form, or one is contained in the other one, or sigma 1 is contained in sigma 2, or sigma 2 contained in sigma 1. So that's the definition. Okay, and then, so second part, let's say that's the second part of this theorem. Is a characterization of the irreducibility of such tensor product in terms of the combinatorics of this Q segment. So let's take this. Then it is simple. So if and only if, so 2 by 2, the Q segments are in general position. So for all I and G, so sigma and I and sigma. So satisfy this condition. Okay, so in some sense, we have proved by hand particular case of this result when we have only 2 factors and n equal 1. So that's the example we have investigated. Very particular case of this. So this results, in fact, so some comments. So it first gives an explicit description of all simples in category. Consequences. So description. Any simple. Let's see. So again, this SL2 case. Pick up some simple module. So you have some Drinfeld polynomials. So you have some roots with multiplicities, and then it can be arranged as a union of 2 segments with multiplicities in general position. And then it gives you a factorization. So that's first consequence. Second consequence is that what we just discussed, that any tensor square of simple module is still irreducible, because if you take a family of 2 segments in general position, then you take again the same family, there are general position one to each other. So any simple V, C is real. So it's again, insist, is real. So which means that its tensor square is simple. Okay, so that's again we saw a particular example in V of dimension 2. So that's some very nice structure of this Grothendieck ring. I was asked, I think yesterday, what go to quantum group and quantum loop. And that's something you don't have for SL2 or classical loop SL2 or UQSL2. Simple modules whose tensor square is simple. So here it appears, and in fact for SL2 for all simple modules. And the last thing I want to state, maybe it's a third part of this theorem, which it is a decomposition of tensor product when the modules are not in general position. So let's sigma 1 sigma 1, I will write it sigma 1, sigma 2. So not in general position. Then there is an explicit relation in the quadratic ring of C, which is of the following form. It is, let's say, we write it like this: V sigma 1, and so V. It's equal to V sigma 1 plus so here I denote by V of such union of Q segments as the simple modules corresponding to such a decomposition. Sigma 5 and sigma 6 are some other Q segments, and which can be explicitly described from sigma 1 and sigma 2. So maybe there are questions tomorrow, I can say how they are defined. What I want to emphasize is that as soon as you have a non-irreducible tensor product, we have an explicit description which generalizes the decomposition we have discussed again for the tensor product of two modules. And again, it looks very similar to an exchange relation. So what we will discuss tomorrow is more precise relations with cluster structure. And I think my time is over.
Are there any questions or comments?
Yes. It is an exchange relations. So this corresponds to two cluster monomials, which corresponds to simple object. That's a way to say it. But it is stated in the theorem. Simple. It follows from the description of sigma 5 and sigma 6, and from this sigma 5 and sigma 6 are in general position. Also a tensor powers. No, it's not. Yes. Yes.
Any other questions? Well, let's.
No. It's here. It's not. So sigma is in general position with itself, because that's again related to the fact that the tensor square of a representation is simple. So, well, to visualize this, you may think about singleton as we did. So if you have just two complex numbers, as we discussed previously. So when is it in general position? It's in general position as soon as the quotient of the two complex numbers is not Q2 or Q minus 2. Okay. So AB in general position. So this is equivalent to say that A divided by B is not equal to Q. Because in this case, the union is a Q segment. But if A is equal to B, it is in general position. And the tensor product is simple, as we have checked for fundamental. So you may really look at to illustrate. So I started with the example before saying the theorem, but you can, now that you have the general theorem, look the compatibility with the example.
Well, if there's no more questions, let's thank David again. Have a coffee break now. We resume at 3:30.